Good afternoon, YouTube, and welcome to the weekend. Needlebender 785 with another exciting video. This one is it's going to be more of on the technical end here. We're going to be doing something called input tuning and tube neutralization. The tube in question here is the iMac 4cx3000, not to be confused with the 3cx3000. This one's actually a tetrode, and it's going to be properly grid driven with proper voltages applied on the screen, stabilized regulated current, as well as negative bias supply on the grid. And that's why we have this decoupling capacitor, because this grid is going to be about negative 250 volts in reference to the cathode. So this tube is very similar to the 4cx5000, which, as you've probably seen, there's a couple of those things floating out there. And by I mean floating, being like the best things to date that me and Needlebender 757 have put together, in my opinion. But this tube is very similar in the way you drive it, the way this circuit works. So this has been kind of a breeze to kind of just replicate what I've already made. But there are some differences. Number one difference is the first tube, the 4cx5000, and it can be run both ways, but the way I had it run is the screen is grounded. Not to be confused with grounded grids and all that stuff. The screen is grounded, but the cathode, which is your filament, which is here, is connected to these. This is filament. So they're totally separate from ground. So the filament was actually negative 1,000 volts. So the screen was just happened to be referenced to ground, not that it was grounded, meaning the same voltage was present as on the cathode. So this one is not like that, and the data sheet recommends it running like a normal tube. Basically, your cathode, the center tap of the transformer, because you don't just want to ground this to ground, that creates some potential issues here, which I'll briefly touch on. But this references the tube to ground at the cathode, just like when you read the data sheet, everything is referenced to the cathode. Now, if you happen to be running a 4cx5000 like I did in my other build, my main amplifier that I run right now, I have just simply referenced the screen as my case ground. Everything else was below that. There was below, the voltages were negative 1200 volts here. So that created some issues with decoupling and having meters having to be read with magnetic what do you call those, Hall effect sensors and stuff, just because your ground wasn't true ground in reference to a lot of this stuff. Now this one in that case is a lot easier. You have your filament transformer hooked up right here, and that the center tap of that is just connected to case ground, obviously through a plate current meter, but it is connected to ground. Now, why do we not just there are some tubes out there, especially like the old Russian tubes, that just simply take one side and put it to ground. The problem with that is that when you're feeding 60 hertz heating current for your filament, you're applying 60 hertz signal. Now, if you're applying it in both directions simultaneously, the waves cancel each other out, and you have zero chance of having any kind of 60 hertz hum in your circuit. Not that I've ever actually come across with that, especially on sideband. I've maybe on AM, some tubes can have that, but simply feeding your main current through the center tab and applying it equally solves that problem by eliminating the 60, by canceling out the 60 hertz hum that way. Also, it feeds your current on one side, and there's some data that has the nichrome wire, that's your filament that emits, especially in these big tubes. There is no the reason why I was actually going to say that, the reason why some of these low power tubes, if you look at the data sheet and you see a low current, something in a magnitude of like 2 to 4 amps to heat the filament, you know that tube is something called indirect heating. So it heats like a metal plate, and that metal plate actually emits the electrons. And that's so in that situation, it's okay to ground one side of it because the actual filament is not emitting any signal. You have something called secondary heating involved, secondary heating. So you have like a metal plate that sits over the filament, and that gets hot. And those tubes, usually the way you can tell, they do have a warm-up time. If you do try to use them right away, you basically get nothing out of them. And trust me, I've tried a GU43B, GI7B, and GS35B that quite a few people out there use. They all have a warm-up time, and primarily it's to heat up that indirectly heated element that winds up radiating the electrons. Most American-built tubes, like the Cymac, uses the actual filament to spit out these electrons. So they're usually consume a lot more current. They're much more beefier, and they have no warm-up time published. I have not seen a warm-up time for this tube. I'm assuming it's. I usually warm mine up, I don't know, at least 60 seconds, but there's no warm-up time published, and it is a very, very high current element. I think it's 40 amps or something like that at 9 volts. So that equates to about 540 watts of heat. That heats up instantly. Anyway, that wire receives your plate current, and if it just feeds it on one side, it can cause electrons to migrate that nichrome in one direction, kind of weakening the, and obviously that process takes time, but you know, why not build something the right way the first time? So we're going to feed our center tap of our filament transformer from case ground through a plate meter, and I'll talk about, it's not going to be an actual plate meter, it's just going to be a current sensor, because this amplifier will not have any meters or switches, as you'll see. And that part is kind of done now. We're working on getting just implementation now. The whole research and development is kind of concluded, and we're at least at the stage where we can start operating it at least in test mode. Anyway, so what we're here to talk about today is neutralization, and I'm going to demonstrate what is neutralization. So the tube, and you can't control this, every tube has something called a internal capacitance. It's a capacitance just simply because of the proximity of different electrodes. Different electrodes being positioned next to each other creates inherent capacitance that you can't really get rid of. So what do we do when you can't get rid of something? You compensate for it. Unfortunately, that creates other issues. Now you can run this tube, as any tube, without neutralization, and I would say 90% of people out there do. And what that does is causes higher intermodulation distortion. And you know, if we're going to be talking about building the best of the best, you know, why build stuff that you know, it's actually only a few parts, but it does, when you're building a multi-band amplifier like I am, it does pose a different challenge, because these neutralization circuits are pretty narrow banded, as I'll demonstrate here in a little bit. They're good for a single band. They'll cover an entire band for the most part, unless you're going to like 80 to 75, because 80 meters is a huge band. You might need to kind of pick where you mostly hang out, and otherwise you're going to have to retune and stuff. But for the most part, this is kind of set it and forget it. You tune it once, and you don't mess with it again. This is how we kind of do it. We are going to have to redo it once you put the lid on, but this is kind of a rough estimate just to see what kind of values I need, because I can't really go on building the rest of the circuit because there's going to be one of these air tuners and an inductor. That's actually an inductor. The reason why it's so small is because for the 10 meter band, which is going to have a 10 meter band, is actually going to be over here. That's the 11 meter band. It's going to have the next band is going to be 20 meter, 40, and then 80 meter is going to be the last one in the corner here. So I'm trying to fit all that in, and each one is going to have an air variable, a little inductor. Now, as you go up in frequency, as you go lower in frequency, your inductor significantly increases, and that's just kind of a byproduct of going lower frequency. You need more turns, so the inductors are going to get more turns, and also capacitors are going to get more value. But the way you kind of deal with that is you have a padding capacitor here. So, but on top of the tube, all we have is we have 4 10 picofarad capacitors rated at 5 kV each in series. So that gives me a voltage rating of 20 kV, which is plenty for what I'm working with, and 20 kV and a value of about 2.5 picofarads. And that what that does is creates a voltage divider with this capacitor, and this capacitor just simply is in parallel with this. Now after this, you have this inductor that just goes to your feed point. That's all there is. This stuff is that's your swamping resistor. So all that stuff is going to be for all the bands, but the stuff that we're working on that we're going to have to implement for each band is just a capacitor and an inductor. That's all we're adding. And there's obviously going to be switching relays, 1 relay per band. So you're going to wind up with five relays toward when we're all set and done. Right now I got 1 band. Obviously this wire's not going to be the way they are. It's just there's going to be a relay. That's all going to go to a relay. It's probably going to wind up being retuned once the relays are in place, because there's extra inductance and capacitance that has to be compensated for. But in the meantime, what we got going on is since I have, for my test radio where I'm at, I kind of have to pull out of my shop area to the main kind of living room area to work on this here, just for the video purposes, because I kind of ran out of room, having multiple amplifiers being worked on and stuff like that. Anyway, so neutralization, what happens with that capacitance, excuse me, that we talked about, is that creates a coupling effect. And the signal inadvertently, basically kind of like a parasitic way of coupling, it transfers to the anode. So you think about it, there's a vacuum there. There should be no signal on the anode, but as you'll see, there's quite a bit of signal out there, and neutralization compensates for that. So let's take a look at that. So we have a oscilloscope set up here, and I'll demonstrate that. So let me zoom in a little bit. So right now, the scale is 100 millivolts per division. So we have a signal of 200 millivolts peak to peak, and this is fully neutralized. So 200 millivolts peak to peak compared to the 40 watt signal, 40 watt dead key that we're putting into this, is about, because 1 watt is 1,000 dBm. So we're looking at so actually 1 watt would be equivalent to about 7 volts peak to peak, and this is 200 millivolts. So this is I don't know, at least 30, 40, maybe 50 dB down from the principal signal. I mean, we're talking about 200 millivolts peak to peak. That's fully neutralized. But take a look at what also, this is our input tune. So take a look at, I'm going to remove, I specifically did not solder this wire. I connected. That goes to those 4 capacitors I talked about. And look at this. Full screen and then some. Now let's just say we were going to take a look and see how bad the actual signal is. Alright, so now unneutralized. So we're looking at 1, 2, 3, 4 minus a half, 3.5 volts peak to peak. So we're probably looking like a quarter of a watt of power passing through. So that's what's a quarter of a watt of 40? That's 4 times 160 times. So 1/160th of power is making it through the tube when it shouldn't be, and that's quite a bit. And that's 1 volt per division, as you can see. And we're almost at 4 volts, so I would say 3.5 to be on the more conservative side. And that's unneutralized. Now all we do is we hook that wire back up. And again, this is not the way it's obviously going to be operated. And we keyed up microphone with the current setting. You can see the line getting a little fatter, but there's almost no, you have to zoom in vertically to actually see our signal. And again, it's less than 200 millivolts. So what is the improvement? So you're looking at 3.5 volts. Let's do the math. For this one, I'm gonna need my calculator because it's gonna be ridiculous to do that in my head. So 3.5 volts divided by 0.2. Okay, so it's a 17 times increase in decrease in the signal. So our signal that's going through the tube is neutralized by 17 times. So I know 10 times is 10 dB, and and another 10. That's about 13 dB of attenuation. So 3.5 volts down to 200 millivolts, and so 17 times. Redo the math here one more time. That's really, I think that's actually better than my 5000. So 3.5 divided by 0.2, and that 0.2 was less than 0.2. So it was about 18 times of reduction in the signal. And as you can see, input tune is flat. So we got this thing neutralized, at least preliminarily, and we're gonna now build on that and add additional bands, and then the whole thing will need to be retuned, like I mentioned. Got holes for these tuners already cut out, as they're going to be facing this way, and our pulley system is going to be mounted here. So this is just kind of the beginning fun stages, and I always like playing with oh yeah, speaking of bandwidth, I'm going to disconnect this stuff. I'm going to have to put the recording device down so we can try to do it one-handed. There we go. Again, I tuned this with the radio and 1.06. And again, the difference, why I've had it before where I tuned it to 1.01. There is difference between applying 200 milliwatt signal from this nano VNA. That's why it's not, I mean, I call this good. 1.06 is fantastic, but Anyway, if you're going to split hairs, there's a little bit of difference between actually applying a high power signal versus this little VNA. There's some discrepancy on that, but as far as I'm not talking about being in the ballpark, being dead on frequency here, we're right there. I mean, this thing is gonna tune out real nice. Anyway, appreciate you watching. I got the blower mounted too. This is a nice EBM blower, same rating as the 5000. A little overkill actually for this. It can take literally 2 of these tubes based on the CFM rating, and the CFM rating actually doesn't mean much unless you actually count in the water column pressure. Any blower that doesn't publish water column is kind of useless in my opinion, because you don't know what kind of CFM it's going to do when you apply back pressure to it. So this one does 1.4 water column at about 180 CFM. This tube needs 80 at 1.2. So we're definitely cooling this tube really good. Anyway, that's all I got for today. We're just going to keep plugging away. Slow progress. Again, this is my personal amp. I'm not selling this. I'm not building it for anybody. So I can take as much time as I want building it, so I can build it right. 73s from Needle Bender 785 here in Florida, back on the side.